Okay, so yeah, so I will start with a brief introduction. Hussein joined my group in 2016 spring semester. So he's been working with us for 4.5 years, more than 4.5 years. So he's been working on developing of wearable sensors for intraocular pressure sensing. Well, actually, he's been working on multiple projects. So one is to develop a contact lens-based sensor for intraocular pressure sensing, and the second one is related to the neural stimulation using optogenetic application, optogenetics technology. And then the third one is related to his internship at the SECONDSIGHT, which is a leading company in the area of the apparetinal prosthetic devices. So he went there last year and then the spring semester and then worked on some packaging technologies. So I think he's ready for the defense. I'm gonna, turn it over to Hussein.
So
Do we have any, before we start, any questions, concern from the committee members? Okay, yeah, Hussein, go ahead.
Okay, so thank you, Dr. Li, for the introduction. And thank you, everyone, for coming to my dissertation defense. So I hereby want to let everyone know that the session is being recorded. So please let me know if you have a problem with that. Otherwise, I would just start. So everyone has the slides in front of them right now, right? Screen, okay. So my thesis mainly started with one big project and then another project the second year got added to it on parallel. And then at the end, as Dr. Lee said, I did another aspect of it. So I created a, so I was, from the beginning, I was interested in vision. So all these three projects are basically addressing vision loss. So, and they are actually using flexible microelectronic technology. So to talk a little about vision, vision is the most important sensory domain of our species, and it's more people than you and I that would agree with this have been surveyed in 2016, around 2,000 US residents, and they all agreed that losing eyesight is basically the most negative compared with loss of limb, memory, hearing, or speech. So it has the biggest impact compared with so many other disabilities. And one of the second leading cause of vision impairment and blindness, basically, is glaucoma. So the first one is cataracts, but glaucoma is the second leading one. So what happens in glaucoma patients is that our eyeballs are basically a balloon. It works like a balloon that has an inflow and outflow of aqueous humor, which is the fluid in the eye. And what the fluid does is it delivers nutrition to the cells in the eye, and it also clears off the byproducts of cell metabolism. So it's really important that there is a constant balanced flow of aqueous humor in and out of the eye. And in this balloon, there's a normal pressure being maintained over time. But sometimes the drainage channels of the eye gets blocked, and we start to have a buildup of pressure in the eye. And then this pressure can cause damage in the optic nerve in the back of the eye, which mainly the retina is located. And this is what happens. So if the eye is not treated, or the patient has not gone through intervention, they start to lose their vision from the periphery. And if it just if it's left untreated, the person can become completely blind. So here again, this is my first project. I am addressing this problem by introducing a wearable contact lens that reads the pressure of the eye and can continuously monitor the pressure so that the patient can be managed accordingly. Then secondly, in the second project, I am working on some technology to study the effect of stimulating the nerve cells of the visual cortex of animals so that we can slow down the blindness that's being caused by glaucoma. And then in the third project, I talk about some improvements that I did on the current technology of creating bionic vision for blind people. So talking a little more about intraocular pressure. So our eye pressure basically changes throughout the day, and usually peaks after midnight, sometime after midnight. And the normal eye pressure is from 12 to 22, but it can peak at more than 60 millimeter mercury at times. So this pressure, it's really vital and important, and it's basically the biggest risk factor of glaucoma. So we want to be able to monitor. So there are three approaches to do that. The main one is tonometry. Tonometry is the long-term, it's been clinically there for a long time, and it's really like they're big equipments that you go to an eye doctor and they find out the pressure in your eye. But then there's implants and there is contact lens. So these are invasive, these are non-invasive. I'm gonna show you a few of them so you get familiar. So tonometry, like I said, eyes and balloon. And the most basic way to find out the pressure is inserting a needle into the eye, which is a closed system then, and then literally find out the absolute pressure. This is what we do in laboratory when we are testing device. And this has actually been there for a long time. It's historically, but it's invasive and you don't want that normally. So there are some non-invasive techniques that are clinically used. So for example, indentation is one technique that you apply a tip to the cornea, and then you measure out the distance that it travels, and based on the force that you're applying, you can back calculate the pressure in the eye, which is a sphere basically. And then the other technique is called applanation. This is a standard. So every other technique is usually compared with this as a gold standard, basically. So applanation, what it does, it works based on the Imbert Fleck law, I assume. So what it does is that it tells you that when you want to find out the pressure inside a sphere, if you apply a force and then you measure out the area that's being flattened using that force, you can find out the pressure in the sphere. So it's pretty basic and very useful and very practical, but usually need topical anesthetic because you might feel that flattening in your eye. You can do the same thing using air puff. It doesn't have to be a solid tip or anything. And then there's this rebound technique that's a little more recent technologically. And what it does is it shoots a tip to your cornea. It's very small, very low force. You wouldn't feel it. And then it measures the deceleration. So when this tip hits your cornea and comes back, the rate that decelerates is correlated with the pressure in the eye. And then using that technique, which does that using electromagnetic coils, you can have handheld devices, which is much better than every other one. And you can have multiple measurements across a day and find out the pressure. So, oops, computer is a little slow. Okay. So let's talk about a few implants. So this is an implant that was developed in 2013 by a research group. And what it does is one of the ways you can find out the pressure, again, you can insert a needle, but then using a capacitance that has a membrane that deflects when the pressure changes, you can have a system, an RLC, that changes its variable capacitor and resonance frequency, and using this internal and external coil and changing the mutual inductance, you can have a readout of the pressure in the eye. It's invasive, obviously, not desirable as much. So there's this other implant that was made by researchers at University of Michigan, I assume, 2011. And this is a great technologically device because it's really small. It's less than a cubic millimeter, and it's got everything you need. You can transmit power wirelessly and receive the data wirelessly. Every 15 minutes, it can make measurements, and then it stores the data. Every 3 days, you can have an external coil again, read out that data from that 3 days, and then wait for another 3 days. Again, you know, because it's invasive, it goes in the eye, and it's capacitive. It has issues. So the battery lifetime is also an issue. So you don't want to, you don't want to put an implant in the eye and after a few months or so want to have another one. So it's always hard to clinically adapt implants. This is another implant that's actually the most successful implant in terms of approval. So it's got the CE mark. It's been used on some humans. So what it does is also capacitively senses the pressure, and using a coil that's in the implant and an external coil, you read out the data. But then again, even there's studies showing that this is causing issues in the eyes of the recipients over time, and it's not ideal. So now we have the contact lenses. Nothing goes in the eye. And for example, in this case, this is the only FDA-approved technology in terms of wearable implants, and it has a strain gauge that works based on resistive sensing, and using coils and an external coil that patches around the eye of the patient, they can correlate their data with the change in the IOP. There's a ton of studies that's been done on this device, and it's basically the leading technology right now, and we are competing mostly with them. So if I put everything I just explained into a table, so this is the iCare Home, this is a handheld device, this is the iMate, the CE Mark 1 triggerfish, and the cubic millimeter and needle couple. So as you can see, we are at the continuous part area of the sensing of the monitoring technology. We also research prototype. We don't have any approvals yet, but our technology is based on strain sensor, which is similar to triggerfish, but ours is inductive strain sensing rather than resistive. So it has its own advantages. And we are fully non-invasive, which is only triggerfish the same. And power consumption, we are at the lowest that any of these devices can be, especially comparing with implant and contact lens, because we're passively doing this, and it's good in that sense. So our accuracy is also what you want. Like usually 1.5 millimeter mercury is like, you don't really need to go lower than that. It's pretty good. So this was encouraging, and then we move forward with our technology. So once you have the pressure of the eye over 24 hours, few days or a few months, So now you're like, what do we do with this? There are different treatments that's been there clinically. So for example, canaloplasty is one that there's a canal around the cornea that's called Schlemm canal, and then every year approximately this is being done on patients with severe symptoms. That what it does, it clears off this canal and helps the drainage of this aqueous humor. And then there's this other technique, it's surgical, and what it does, it literally like removes some of the trabecular meshwork that gets clogged in these patients to enhance the drainage of the liquid. And the other technique is you can, using laser, you can burn off some of the ciliary muscle. So these muscles also are responsible for generating and the inflow, they help the inflow of the aqueous humor. So by burning off some of that muscle, you decrease the creation of aqueous humor or the introduction of aqueous humor in the eye. So you're decreasing the inflow. And if it, apart from these surgical ones, so we have this half surgical, semi-surgical one that you can insert these stents, eye stents. So they're literally like you're piping out, you're creating a larger pipe using these metal stents to encourage the outflow of the aqueous humor. But if you don't want to deal with any of these surgical ones, like one of the most common treatments is also pharmaceutical. Like you can have there's two categories of eye drops. There is beta blockers that they inhibit the ciliary nerve, so you inhibit the inflow of liquid, or you can also, using these other category, prostaglandin, you can encourage the outflow. So we're hoping our device could help to regulate and manage the use of these eye drops for the patients. So to dig in a little deeper to our technology for the contact lens, as you can see here, we are creating a wearable device. So the sensor sits inside this flexible contact lens, and the person can get them in one or two eyes. And then the reader coil can be placed inside a pair of glasses. And we are able to eventually, technologically, it's possible. Like we haven't fully developed the goggles, but it's possible to get the data out of it and to your phone directly and continuously monitor the pressure. And again, in our system, we are using RLC. We're using a resonant tank. But instead of changing the resistance or the capacitance, which causes issues like leakage and drift over time, we are using inductor, variable inductor, which is way more robust and basically less affected over time in terms of mechanically and electrically both. So yeah, so, and then using this external coil and the impedance analyzer, we are reading out the change in the mutual inductance of these coupled inductors. So yeah, that was the idea. So when I started this project, I looked up, yes, we can do this theoretically. You can change the area of an inductor and use that as a sensor, basically. Read the change in the resonance frequency. But I wasn't sure if this is gonna work. So I ran some experiments, so very basic ones. So it's just a wire and an SMD capacitor within the dimensions that we are interested, and it's 4 picofarads and around a centimeter, 1.5 centimeter. So I got this beautiful resonance frequency, 350 megahertz, and then by just deforming the same device, I decreased the effective area of this coil. So the current is, for example, passing clockwise like this, and then the effective area is decreasing. And the more the effective area decreases, the resonant frequency that I'm reading off this device is increasing. So that was great. That was really encouraging, made us move forward. I wrote some image processing on MATLAB how to basically find out the change in the area, and showed that the results we got experimentally fit really nicely with the theoretical formula using the formula for inductance and resonance frequency of RLC tanks. So we got a really great fit. And I did two scenarios. The first scenario, we had the same length of the inductor. And using deformation, we were changing the area. It worked really nicely. And then I also was just curious what happens if the shape is the same, the length gets shorter and the area changes accordingly. And it also worked really nicely with the same formula theoretically. So it really didn't matter. Because basically in our case, what's happening is this one, not really this one, because in the inductor, the stretchable wire, what's happening is effectively the length of the periphery of the circle is changing, and that's how the area is changing. So I ran some electromagnetic simulations to look what's really happening with a coil like that. So these are some interesting visual simulations that I got off console, and it shows how like two coils would communicate and get inductively coupled. It was more like a qualitative simulation rather than, but I also had the right dimensions. Like this is like the same, like, and what we got quantitatively of the simulation was the value of the inductor, which really fit with what we were anticipating, which is around 50 nanohenries. So in 50 nanohenries is about what you get from a coil that is 1.4 centimeter in diameter. And that was nice to verify with simulations. So this is here, I'm showing two main masks that I use. This is the first generation of devices we made, and then we also made like larger ones to compare. I'll talk more about them next. So in terms of mechanical simulation, I ran one simulation at the beginning just to figure out when we are having this stretchable wire made out of solid thin film metals, how are they gonna behave when they get stretched, and where the stress points are, and how can I adjust the design so that I overcome some of that stress. So when I ran simulation in 2 dimensions, so in both dimensions, I realized that this is a weak point. So when imagine this gets stretched from the 2 ends, and this point is gonna break earliest over time. So what I did, the way I adjusted my design based on this simulation is that I made this part of the wire thicker, like wider than this part, just to have more room for the parts that over time gets damaged, and it so that the overall width that electrically passes current wouldn't really get affected as much, because the less wide this gets, the resistance overall is going to go up. So you want wider part here. So that's what I learned from the mechanical simulations. And let me get us to the fabrication steps real quick. So the materials I used was silicon as a substrate, Parlinsi as the packaging material, titanium as the adhesion promoter, gold and aluminum, and obviously photoresist as the photolithography element. And so the first part of the fabrication, I created the main wire by shaping the first layer metal, and then I applied the second layer metal for the top of the capacitor. So the capacitor has bottom and the top. So this creates the top layer of the capacitor, and then I created an opening to create a connection between the second and first metal. And after that, I deposited the third layer metal so that I create the connection that I wanted to get from the second and first metal. And this is how it looks from the top view. And this is the side view, by the way. And yeah, and then I eventually covered it with Parlin C for a last step of packaging, and then I released the device by creating these aluminum metal masks so that I can dry etch the entire residual Parlin C. And then when I did that, I released the devices off the wafer, and using cast molding, I created these contact lenses. So here's a quick look at what happens in terms of cost. So I'm using gold in the final design, and I made a calculation that each of these wires, each of these devices would cost around $4.50 of gold. So it's not too expensive, not too cheap. And once I made the devices, the first way I tested them was literally attaching them to a balloon, like a birthday balloon. And I put the device on it, and using PDMS, which worked like a glue, I completely attached the device, and I read a really nice shift of the resonance frequency, which is this point, to the left. So the larger the device got, the lower the resonance frequency was, and that was super encouraging, showing that the sensor itself works as we expected. And then I was like, how can we, I was really curious about exploring other geometries. Like, what if we have multiple turns in different forms and geometries? But the problem was, once I built them and I tested them on 3D domes, it looked like it's really difficult to create a two-dimensional geometry and then place it on a 3D dome. It's challenging. So we postponed this for later, but it's something nice to always, if you have 3D printing technology we can use, you can create something like that on a 3D substrate, and then that would be nice. Another thing I explored in different types of geometry was, what if instead of having a full contact lens, we have a contact lens that has only 4 legs, like this? Because when we're placing the sensor can be really sensitive. But then when we encapsulate the whole thing with the contact lens, we are limiting its stretchability and its sensitivity. So if we have just 4 legs that are encapsulating the sensor, but we have 4 parts that the sensor is just floating in air, and then when it sits on the eye, it's really just free to stretch. So what happens is that when the eyeball, the cornea, expands, when the pressure changes, these legs are going to get further from each other, and these parts would stretch really nicely. So that was the idea. I built some of those devices using this type of mold, which I customized. So what I did is that I placed a sensor around it, I poured PDMS, and these parts are blocking the parts that you don't want PDMS there. And then they won't get encapsulated. And then you release the entire contact lens. I put them on an eye, I tested them, but again, there's wrinkle issues. There's so much fine tuning that needs to go into creating these clover-shaped devices, which we call them. There's also the larger devices, like I mentioned. We wanted to see, when we have larger eyes, what's going to happen. So we created these large devices. So it's important to explore and find out you have working devices in different dimensions, because if the dimensions change, everything changes. You have to really like optimize the width of the wire, the length of the wire, everything. So it's important to have different dimensions that you're sure it works. So what I did, I placed these sensors inside a PDMS membrane, and then just to see how well the sensors are functioning, and I got really great results that showed like a little bit actually more responsivity when the wider wire is being used. So, you know, when the wires get wider, you have better electrical performance, but you have less sensitive mechanically. So, but overall, it gave us a better responsivity. So it was interesting to compare these, and it's good to see they work really well if you have larger eyes. So this is the setup I used for sensing, for testing these devices. So I created this chamber that using this T-junction, I am applying pressure and controlling the pressure in this guy and see the change in the diameter of the sensor. And this is another side view. This is another test, similar, but on the original size of devices, which I did. So this is the chamber, and this is the change in the radius of curvature of the membrane. So this is similar to what happens in the eye. So if this orange part is the cornea, when the pressure of the eye changes, the cornea becomes like this. So this is what you're sensing basically using this technology. And yeah, this is there.
And may I ask you a question?
Sure, go ahead.
So in this measurement, I guess the distance between your sensor and the pickup coil, is it fixed or is it changing because of the pressure?
It changes, but I also changed the reader coil height to keep it constant between these measurements, but it wasn't really like, I couldn't compensate as much. So you can see there's like a stronger signal at higher pressure, you see?
Mm-hmm.
So at higher pressure, I got closer to the reader coil, the higher it got. So this is a common thing we always saw, that this happens if you don't compensate as much.
So basically the change in resonant frequency is it dominated by the spacing or more due to the change in the inductance of your coil? Which one dominates?
Yeah, great question. So I have done tests to here, I can show you. So in order to isolate these factors, I did separate measurements. In one measurement, I had a sensor, and then I only changed the reader coil height. And then I realized when you change it, the strength of the signal changes, but the resonance frequency is always at the same position, okay? So when we have so we are sure that the change in the reading distance doesn't affect the resonance frequency. And that makes you feel sure that when you have a change in resonance frequency, that's due to the change in the diameter of the sensor rather than the reading distance. And the same goes to the reading angle. So when you have contact lens on and you look left and right, it's gonna have the plane of the sensor and the plane of the reading coil are gonna have an angle that changes a little bit. And I did some extreme tests, like 30, 45, 60 degrees. And I also realized that by changing the angle, again, the strength of the signal changes, but not the resonance frequency. So these are really good control experiments that show that it was encouraging, because we also had the same concern you just mentioned. Okay, so did I answer your question?
Yes.
Okay, thank you. So a top view, again, you can see when the, so here's the 4 measurement points. Okay, this is let's say this is a device at rest. When the pressure goes up, this device is stretching, and the effective area that's inside the coil is increasing. And when that happens, the inductance is going up and the resonance frequency is going down. And this is, we actually literally simulated these same dimensions with the same thickness and material, and we got the accurate inductances from simulation that actually correlates really closely with the experiment. So when the coil is getting stretched, you can see that how it's affecting the electromagnetic waves and the change in the inductance. So also in this experiment, I did a multiple cycle test. So I expanded the chamber and deflated, expanded, deflated, expanded, deflated. And then I realized every time the device is almost coming back to the original point, which is really good. That's what you want. And this is just one cycle zoomed in. And then we were ready to test it on an animal's eye. So we started with a dog's eye, and these are some closer view of the devices with the device that we use on the dog's eye. So this is the setup. And so we place the sensor on the dog's eye, and then using a needle, we pressurize the eye and read the pressure using this pressure meter and control it with this syringe, and got these results and at 35 kilohertz per millimeter mercury. And then this is a year after I got this rabbit's eye test, which we made this contact lens a lot thinner, and we tested on this rabbit eye, and we got like a lot more sense responsivity, like from 35 to 635 kilohertz per millimeter mercury. And then I wanted to see what happens if the humidity in the environment changes when you have these devices on. So I changed the relative humidity from 70 to 90 something percent, 92 or 3, which is very typical in Michigan, I guess. And then I observed that when you change the humidity, the resonance frequency follows that fashion. And then when you decrease it, it drops back, and then same goes again. And so I infer from this experiment that you can compensate. If you have a humidity sensor in your, let's say, goggles, in your electronics, or you can, and if you know what the relative humidity of the environment is, you can recalibrate every now and then your resonance frequency. So I wouldn't be worried too much about change in humidity. And same goes for temperature. So I put the device on a hot plate, and using a laser thermometer, I saw that when the temperature goes up, I ran 4 episodes. Temperature goes up, the resonance frequency goes up, and it follows likewise for other episodes. So I also infer that you can compensate the change in temperature. Okay, and I did some programming to make the interface a little better. So this is a software we were deriving the data from. It's an open source software, and this is our impedance analyzer. So the data goes to the computer through a GPIB cable. But the problem with this software, as great as it is that every time you run it at a specific pressure, high pressure, you're just getting one file for one data point, and you have to manually run it every time you change the pressure in the eye, and then import all those files and spend a couple hours in analyzing them and getting the change in the resonance frequency. So every eye that I tested, I spent 3 hours after that to just process the data. So getting help from our great undergraduate researcher, collaborator, Ryan, we customized the code in this program so that you just tell the program how many measurements you want. Let's say you want to measure your eye at 10, 20, 30, 40, and 50 millimeter mercury. Okay. And you know that you're changing the pressure every 10 minutes, every 2 minutes. So you just say 2 minutes of delay and 10 measurements, and you press run. And it just generates all the files. And using the MATLAB code that we wrote, it also automatically imports all those files and gives you the final change in resonance frequency by fitting different mathematical functions to these and minimizing the error every time. So now the program is ready to go. So future directions, this was so far what I did. And what's happening right now is that we collaborated with a company in Michigan that is creating an impedance analyzer that's handheld. and basically replacing this giant benched up impedance analyzer with this guy so that we can test the devices on rabbits that are living. So in vivo testing, it's what's scheduled and happening in continuation of this project. And the progress so far has been published twice in a conference and a journal paper. You can continue and read them if you're interested to learn more about the technology of this device. So yeah, and here I'm ready to move to the second project. Knowing the pressure in the eye helps to manage and prevent the blindness that's caused by glaucoma, okay? But there's another technique that's recently shown promising, that you can slow down the degeneration of retinal ganglion cells that is usually associated. Oh, sorry, it's my Siri talking. So optogenetics, like stimulating the brain cells in the visual cortex of animals, has shown that they can slow down the degeneration and death due to apoptosis of retinal ganglion cells that cause blindness eventually. So in order to study that hypothesis, these early studies further, and hopefully making it move towards a clinical treatment, we wanted to create a device that's really small. It gets fully implanted on the heads of animals, mice in particular, and we can test multiple experiments. So this is the latest results that show that correlation. So when you have a glaucomatous eye patient, you're here. So this is a survival rate of that model versus normal. And then you can apply BDNF, which is a protein that helps to reduce the death rate of these retinal ganglion cells, and it's a pharmaceutical treatment. And then if you combine that with an optogenetic stimulation, this study was done in 4 rats, I assume, recently in Dr. Weber's team, and it showed that we can enhance this therapy a lot further. So in order to do that, we need to make something really small, and it's wireless so that you can run behavioral experiments on animals. So I dig down and found the smallest Bluetooth chip on the market, and then we created this substrate that's flexible and has this tip that you can put the micro LED on it that you can stimulate the visual cortex with. And then the small battery would run the entire system, and using a cell phone, you can control it. So this chip is all inclusive. It's got an ARM cortex, it's got the antenna, the converters, and all the RAM unit. So everything is just here, all packaged. And then you can just, we tested and we realized, wow, yeah, you can actually drive enough current out of this chip to drive these micro LED. So we tested those LEDs. I'll show you in the next slide. So this is the first generation of the device. It was a little too big, we realized after we tested it on the rat. And then we created the second generation. So this is a micro LED and the tip that would stimulate. So these are the results we got from testing the LED. So we realized, you know, this is actually a diet curve that we expected to see from the LED. And then the intensity of light, most importantly, was doing great, because you want more than 1 milliwatt per square millimeter to make sure that you are you're stimulating activity in the nerve cells. So after around 4 milliamperes, you can get that, and we can go up to 9 milliamp using this chip. And also we studied the change in relative temperature that is also rather stable. So these were encouraging. So we moved from here to here. We implanted the device on a rat, and the device was larger than it could completely be implanted. That's why we created the second gen that's not been tested in vivo yet. But here we realize that yes, this works. So this LED, this is brain cells before stimulation, after stimulation. So you can see that the LED is stimulating the nerve cells successfully using CPOS sectioning experiments, and it was encouraging. I got published and everything. So yeah, and future direction. So what happened? This chip got discontinued at some point. We found a smaller chip. We have been programming it, and currently that's where we are. Like, we have successfully programmed this new chip, and we are at the packaging part right now. So and then very recently I've seen also like a smaller chip that we could use eventually. So you always want to go smaller and smaller. So in my third project, which I went to internship to SECONDSIGHT, I was lucky to work on these devices that has already been on market. So these devices, what they do is that they're artificial sights. They create bionic vision for the patients that have been blind, in many cases more than 20 years. So they start to see grayscale vision, black and white, the borders of objects, and bright versus dark areas, and it increases their autonomy and independence as patients, as blind patients. So the first generation of this technology was placing electrodes in the back of the red eyes of the patients, and it was stimulating the optic nerve directly in the eye, using and taking the vision, taking the image of this small camera, and then using a 60 electrode array stimulating. And this was called Argus-2, and it has been implanted in 350 or so patients over. And then recently they started trying stimulating the visual cortex of humans directly. So this is the second main generation of the devices. So this, because the first technology only helps people that got blind with retinitis pigmentosa, but that is a really small portion of blind people in the world, and not every blind person can use this. But this device can be used by all blind people because it is directly stimulating the visual cortex. So I went to this company and I was like, how can we improve the latest thing you've made? So the problem is, they're not the problem, but the bottleneck of the technology is that right now people don't see colors as much, don't have a high resolution vision. It's really small. How can we increase the resolution? How can we induce colors? These were the questions that we were asking. So I started to look at the coating technology of these electrodes, because when you want to increase the resolution and induce color, you want to get a higher density electrode than what currently exists. And in order to do that, in general, coating of these electrode sites are everything. They're very defining. And when you get to smaller and smaller electrode sites, you want better coating so you can inject enough, electron into the neighboring tissue. And that's a big technology bottleneck at the moment. So I looked at some of the latest research in academia and realized PDOT, which is a conductive polymer, is really great at cellular agreements with the cells, biocompatibility, and also has a really high charge storage capacity, which comes from the nature of this material that allows the movement of electrons and ions at the same time. So anyway, if you look at, this is the electrode array that was used in Orion, the visual cortical implant, and I took those and And if you look, this is like a bare smooth platinum electrocyte versus platinum gray. So this technology already turns a blank platinum into these 3D geometry. So to increase the effective surface area. So the company already had a solid state technology to address this problem. But in order to go further, I use platinum. I use PDOT. So if this is bare platinum and then you coat PDOT on it, then great. You already improve everything a little bit. But then you have platinum gray that was already also there, and platinum gray also helped the technology a lot. But then what if we, so I combine the platinum gray and PDOT to see what happens and what we get out of it. So I ran a lot of electroplating PDOT first on platinum, and I realized that when you have platinum PDOT at different thicknesses, you have higher charge storage capacity and with these CV measurements. So here you go, like I electroplated PDOT on each of these different thicknesses, and then I had platinum gray. And you can see here that platinum gray and PDOT are a little comparable in how much they improve. So this pink one and the green one, you can see like, but then when you have more PDOT and platinum gray, this red curve is what I got from combining the two technologies. So a lot more charge storage capacity. But then I wanted to see how well this coating lasts over time. Because the PDOT issue, the main one is adhesion. So once you plate PDOT on smooth platinum, it's so easy, they come off so easily after a few days under stimulation in PBS, or even using a Scotch tape, you can easily peel them off. But then I ran a technique, also learned from Dr. Martin's group. He's famous in PDOT research, and he recently also came up with this adhesion promotion technique, which is chemical. So using diazonium salts that I also synthesized myself from his recipe. So you create some covalent bonding between the PDOT molecules and the platinum molecules, and that increases the adhesion of this coating a lot more. So I did that, and I realized after 3 times by using Scotch tape, I couldn't peel them off. So I also tested them long term, and then I was like, okay, platinum gray and PDOT together are great in terms of charge storage capacity. Let's see platinum gray if it's also helping with the adhesion. So I did the chemical adhesion promotion and electroplated PDOT on platinum gray, and which creates a hybrid scenario. So if you look at this, because you're creating a chemomechanical situation. So this orange one is already creating covalent bond between this PDOT molecule and the platinum gray. That's already improving adhesion. And overall, this maze of 3D geometry in general is working great at encapsulating and entrapping these PDOT molecules. So you're also mechanically improving the adhesion promotion here. So I ran long-term tests, and I realized, yes, when you have platinum PDOT, diazonium salt chemically helps to have less of a decrease in electrical resistance over time. And also, when you have diazonium, your capacitance, which is improved already from here to here after you plate it, it drops a little slower than when you don't have diazonium salt. And then in case of platinum gray, first we had just platinum gray, okay, over time. And then we had the PDOT. You can see electrical resistance drops. The second day 2 is when I plate the coating. And then you go on, it pertains its improvement. And then if you have platinum grade diazonium salt and PDOT, it drops, but over time, it really helps to keep the low resistance And same goes with capacitance. Again, platinum grades here, you increase the electric capacitance a lot more when you have PETA, and then when you have diazonium salt added to it, you pertain the resistive or how good this coating is lasting is lasting after even 495 days or so that I ran the long-term stimulation, 452, excuse me. So yeah, and then in terms of future directions, let me just show you one quick video. When you want to increase resolution and induce color in implants, you want to insert electrodes. But if the electrodes are flexible and they are even softer than the brain tissue, how do you insert them to the brain? You can't do that. You need to, one of the ways I investigated in the company was using silk fibron. You coat the electrode and you stiffen it. Now it's stiffer than brain tissue. You can insert it, and then after the electrode is inserted in the brain, the silk fibron dissolves, and then now you have this soft electrode. That's really nice and smooth, not damaging or anything. So here's the electrode. You can see I tested the insertion into cow brain. So now I'm moving forward. Haven't reached the surface of the brain yet. And now you can see the probe is being inserted. Without the silk fibron, you couldn't do that. Like, it would just bend and never be inserted into the brain. But now it's being fully inserted. And this other video shows the outward motion. So once you're in here, now I'm pulling it off. And when you pull it off, you see how softer the electrode has become. So this is in terms of future direction. That's the stuff you want to do for that. And this also article was written and recently submitted to Advanced Materials. And thank you so much for listening. Any question, Dr. Lee?
Thank you, Hussein. So we have one question from an audience. The question is about the coating material you used in the last project. Can this type of coating be used in other types of intrabrain technologies effectively? If so, what kind of applications do you expect it could work for?
That's a great question. Yes. As I explained in the article we wrote, this technology can be used in every stimulation and recording application. So anywhere that you need a really high capacitive interface between the tissue and your electrode and lower resistance, you're gonna need to use this. This is like inevitable because this is the direction that you want to go. Lower impedance, lower resistance, high capacitance. And this is what this is offering. So it doesn't really matter you're recording or stimulating.
Okay, so I think Aaron had a question because I saw you raise the hand. Oh, okay. Sorry.
No, I was clapping.
Oh, okay. All right. Sorry. Any questions? Any other questions from the audience? So you could use the chat option, or you could just speak up. Okay, there's another question, which is following was the previous one. Okay, so it's about the how to extend the lifetime of the electrodes to long term, like 10 years or above. Do you have any comments or thoughts?
Well, actually, at 452 days, my internship ended. So if I could stay there longer and test the devices a little longer, the devices really didn't completely degenerate at that time. So when you have platinum gray and diazonium salt with PDOT, they already pertained a fair amount of performance that was improved. So that was really like, we don't know. This current, the same thing I created could potentially work for longer terms. But if you really just like want to push this even further, I mean, again, you want to look at the different dopants that we electroplate PDOT with, because right now what I'm using is PDOT is a combination of EDOT monomers that I electroplate and combine it with, you can use like PSS, I use BF4, like tetrafluoroborate. But if you use other dopants, this can affect how well the PDOT can function. And also there's so many different things you can change during electroplating. You can electroplate galvanostatically, like I did, by constant current and changing the time, or you can change the current. You can have variable current. And each of these changes in electroplating can give you different characteristics of the coating. So this coating is not highly tuned and modified necessarily in terms of electroplating, how well to enhance the long term. So there's so much to do and explore to increase the long term stability of the coating.
Another question, there's a biocompatibility response.
Right. So PDOT has been shown to have really good cellular agreement in general. But again, what dopant you use in PDOT changes its biocompatibility. For example, I use tetrafluoroborate, which is great electrically and chemically, but then at the end of my internship, I realized it's really not that biocompatible. So then I was a little disappointed, but then you know, you can switch back to PSS, which is maybe a little less electrically advantageous, but is like shown the most compatible version, biocompatible version of the PDOT. But then again, you have platinum gray itself that has been shown biocompatible and stable for more than 10 years already by this company. So if you have those as a substrate, you don't want to be worried about the platinum gray. And if you want to worry about PDOT, you have to look into what exact molecules you're using as secondary dopant, because each of those changes the game. And as far as I looked in the literature, there's no like long-term biocompatibility PDOT tests specifically to show. So it's yet remained to be seen.
Yeah, I just realized one thing. Do I need to unmute people if they want to speak? Is this a meeting or a seminar?
This is a meeting.
So technically, they should be able to unmute themselves, right?
Right. Yeah.
Okay. All right. Sorry, I didn't notice that. Yeah, I think it's a good comment, because when you have a biocompatibility response, it's not only for the lifetime of the device, but also for the recording quality. So you will see the degradation of the recording quality or stimulation performance over time. So.
Right.
So there's another question. Can there be other metals used other than platinum for those electrodes?
Yes, there is iridium. That's pretty good and very popular in the field. Yeah, there's a couple others. There's platinum, iridium. Yeah, I have to look it up. It was like a couple more. But yeah, iridium and platinum are pretty leading, especially iridium oxide. It's really good. And I would want to study that a little further. There's like more established metals, but iridium oxide looks really promising. I would want to research that. Yeah.
Okay, any more questions from the audience? If not, so thank you very much for participating Hussein's presentation. I will ask you to leave the Zoom so we can have the committee discussion. Thank you.
Thank you everyone for coming. Hmm? Not everyone has left yet. So I think
There's a Galaxy S9. I'm not sure who's that.
I'll be back in a minute.
Okay, so
Can you close them out as host?
let me. No, I won't be able to close them out. I could put them in the waiting room. Oh, I could remove them from the Zoom. Okay. Huh? Let me do that.
Galaxy S9, I don't know who that is. Yeah.
I don't know. I'm removing people from Zoom because I don't know if they're still there.
Right.
Let me check. Okay, I think we're good to go. So, questions from the committee members. Art, you want to start?
Sure, saying that's nice work. The first part I could have partially slept through since we spent a lot of time together working on that. I have a question with regard to the temperature and humidity as measured, you know, on the benchtop versus the real world, and particularly with regard to temperature, where you know, with the contact lens against the eye, is there much change really taking place temperature-wise, or is it being maintained by the body? You know, we did this several years ago in a different study where we developed a little fan and heater control, et cetera, and we're looking at the changes in temperature. And the eye seems to maintain. Now, maybe we were thinking more along the line of an implantable device, but so are you mostly looking here at the changes in temperature from, you know, you're outside in the sunlight, etc., or to what extent do you think that it can be compensated for by the body temperature and its effect on something that is so close to the body?
Right. I guess the test that I ran, I agree, it's pretty extreme, like up to 40 Celsius. I don't think the surface of the eye would ever, probably not. I don't know. But that's a great question, like, because I know that the surface of the eye, there's already a temperature regulation happening in the eye due to the convection of the aqueous humor itself. So in what extent that's being really compensating that, I'm really not sure. That's yet to be studied. Maybe it's not that extreme. Maybe it is. Maybe it changes from one person to another. Yeah, I don't know.
It'd be interesting. I don't know if you could do it with an infrared thermometer. I have one. I may have to. I may have to find a guinea pig and try this on, since it's probably hard to do on myself. But it'd be interesting to know whether there is a lot of change there, or whether, even, a person wearing a pair of sunglasses would basically shield the device from any kind of extreme temperature.
Yes, that'll be interesting to see.
That's my question for now on that. I just had to pull up your thesis here to look through the notes that I put on, tagged on it. So.
Sure.
So, Pran and me, which one? So, Pran, me, do you have any questions?
Sure, yeah.
So go ahead, Pran.
Hello, how you doing? You want to go first, or?
You go first, please. You can do that.
Thank you.
Yep.
Okay. I got a question related to the early experiment you did where you were kind of bending the wire, changing the cross-sectional area.
Right. That's
I
cool.
think you're using this thin wire.
This one?
Yeah. In this case, you saw a change in the resonance frequency. And
Yes.
what about the Z direction, in the sense that assume that when you bent it, it was not flat, correct?
Right. Yeah.
So,
Not perfect flat necessarily. Yeah.
so was it sensitive to that aspect?
Well, like I assume it's going to be the same effect as similar effect to as when you have an angle between a reader coil and the flat or a little not flat sensor, because it's definitely going to affect the electromagnetic field and the slightly change. Maybe like if you have like let's say that the formation and the area is exactly the same, and then one of them is flat and the other one is slightly bent, I would be sure that the one that's bent is gonna show as if its area is a little less. You know what I mean? Because the perpendicular electromagnetic field that's being coupled between the external coil and the sensor coil is going to be less effective, that mutual electromagnetic field, and it's going to affect that negatively. That's how I would model it in my mind. Yeah.
Okay, that's fine. I guess in the later on you showed where the change in resonant frequency was not affected by the distance from your coil, interrogation coil to this resonant structure. So that's okay. Another one related to this one. So this is just a simple wire that's kind of soldered together, or what is it? Just be a little bit more. I don't know if you mentioned.
The capacitor at 4 picofarads here.
Okay. Okay. So you do have the capacitor there. Okay.
Right. Yeah.
So you're making it an LC resonant tank on that one.
Yes. Mm-hmm.
Okay. And also, I mean, you did a nice background study of where you compared where other people are doing, sensitivity based on change in resistance versus change in capacitance, and you're doing it based on inductance, correct?
Yes.
So have you kind of compared it as to which one would be more sensitive as to sensitivity analysis?
Well, you know, for example, yes, the capacitive, the cubic millimeter technology, which I showed, has the lowest among the ones that I'm presenting here, which is at 0.5 millimeter mercury. Yeah, it's we could go that close, like depending on our impedance analyzer, because the sensitivity is a tricky game when you're working with these sensors. So when we say 1 millimeter mercury, this is what, you know, we get from the type of analysis we do on our data. For example, you know, we are looking at 35 kilohertz per 1 millimeter mercury, right? And this is the worst we have got. Like every other test we've done, we've got better results, more kilohertz per millimeter. So at lowest, we have 35 kilohertz of change in resonance frequency that we are sensing. But now, it solely depends on your impedance analyzer and your back-end electronics and analysis, also data analysis, like how small of a kilohertz of a resonance frequency now you can detect, depending on the type of impedance analyzer you have. If you go really small, you can go up to like thousands of millimeter mercury easily. But then again, the question is, do we really need that? Also, probably not, because clinically, as far as, you know, if you got a change of 2 or 5 millimeter mercury, you're going to be fine. If you tell the patient that your eye pressure moved from 20 to 60, that's what they want to know. They don't care if it moved from 2 to 61 or 61.1. They really don't care. So clinically, it's really not that critical and relevant to go really small and sensitive.
Right. So, you know, if it went from 20 to 28, they would have a concern and they'd want to know, you know, 21 is kind of the magic number of which somebody becomes considered a potential candidate for it. But one of the things that's confusing here and why these sensors are needed is that half of the population has pressures that are higher than the 21, which has historically been established, and they don't develop the disease. And the other half have pressures that are under 21, and they do develop the disease. So there's a new thought with regard to the biomechanics of the eye that are also involved, and have the pressure is, you don't have to have high pressure if the biomechanics are not good.
So in that respect, I guess, when you, let's say if somebody has a high pressure to begin with, so is this the change in resonant frequency linearly dependent, or is it going to saturate? Because let's say if somebody already has a high pressure and there is a small change beyond that, would it be sensitive to that, or is it a linear behavior still beyond certain pressure?
What do you mean by a high pressure to start with?
Let's say the number you're mentioning, 21, 20, those kind of range. Let's say, so somebody has it, and then you want to see if there is an increase beyond that, versus somebody who has a normal pressure and a change of 1 millimeter mercury, basically, let's say. So in a sense, the question is this this sensor linear, depending on what pressure you're starting from? Or do we have to design a custom for everybody else, everybody who wears it?
That's a great question. I have studied that. So the sensor itself is linear within the range of 0 to 60 or 80 millimeter mercury. I've tested that. It's pretty linear. But now the question is the eye, because what we're sensing here is the train of the cornea, right? But now the eye, is the eye linear? And what's the range that the eye itself is linear in terms of transferring the change in the pressure into the change in the strain of the cornea? There's like studies done before me. So, and also I observed it myself multiple times. The eyes usually 35 millimeter mercury, they have almost a linearly detectable change in the cornea, the angle of the cornea. But then after that, the cornea gets really stiff, and actually in the eye, biologically, what happens is that another pathway of drainage of the liquid opens up at that point, which is called uveoscleral. So there's two main drainage. There's the trabecular meshwork around the cornea. That's one pathway for drainage. The other pathway is uveoscleral. It's literally water coming out through the sclera. That's what happens.
Through the uvea, through the iris.
Through the iris?
Right, not through the sclera.
Not the sclera? Okay, thanks for correcting me on that. But yeah, what happens is that the cornea doesn't really deform as much after 30. And then using this sensor, we cannot detect it more than that, as accurate and linear as we can before 35.
So there is no so there has to be better references to where this can be used, or to as a starting point as well, because you're looking at a change in where you start from, but you don't know where you're starting from to begin with, one, and two, then beyond certain point, then it's not going to sense as well. So there are a few limitations.
Absolutely. In terms of the principle of the measurement we are having in general, because if you want to be, like in principle, if you want to know the absolute pressure in the eye, you need to get in. You need to either a needle or using manometry or needle coupled implants that I showed. You can always find out the absolute pressure. And then the second better technology is capacitive. Again, that capacitor chamber that goes in the eye. And then, there's so many other ways, like there's optic techniques. There are implants that they are attached to the back of the eye, for example, and it's like a diffraction grating. It's like a small film that has diffraction grating. And then when the pressure changes, the separation, the gaps of these diffraction gratings change. And then using an optical camera out of the eye, you can monitor that film and tell the pressure, for example. That's another way that correlates the strain again in the eye. So there's so many different approaches, and each of them has its own, yeah.
Okay. And kind of related to that, is that you want to make it eventually this thing is linked to a smartphone device, right? A smart device. And you also kind of alluded already that it depends on your signal to noise, or how sensitive it is, depends on what kind of a impedance analyzer you got, right?
Yeah.
So what is the best change in frequency can you pick up using a smart device versus the equipment you're using? The equipment you're using is probably one of the best out there, right? So how close can you get to that? I know you showed something that somebody in Ann Arbor is building one, commercial. So what is the sensitivity of that versus the instrument you're using? And how good can we get it if we couple it to a smart device?
Great question. I don't know. It's yet to be seen. Have they tested? Dr. Weber recently, I've been talking to them.
The Michigan device is the implantable MEMS device, right?
No. Interbeing, the portable impedance analyzer made by Interbeing, have they shown how small of a change in resonance frequency can they detect?
What is the frequency resolution, basically?
Yeah, like, you know, the steps, like 10 kilohertz or 100 kilohertz, like, or is it 1,000 kilohertz, that the smallest change in resonance frequency they can detect.
Mm-hmm. Yeah, that'd be one. Yeah, that's one thing to watch out when you're going to, you know, if you're going to take it to the next level. That's a big challenge and question to ask. What is the sensitivity can you get? And based on that, you may have to redesign the coil to, you know, get a change in your inductance as to what leads to that. You know, the minimum change in frequency that you want to pick up. So those.
Ordering the specification, I do remember I required minimum of 50 kilohertz, and they were like, so.
Yeah, so that number was actually calculated from the curve fitting. So because your instrument has a very poor resolution for the data collection. So when you do the linear fitting of your data, so you back calculate the sensitivity of the device.
That's true. That's true. But also, it doesn't necessarily affect, because if you can't do the curve fitting that's really sensitive, let's say you have a range of 5 megahertz, for example. You know, depending on how many data points you have, you can have, you know, smaller steps. So yes, when you're collecting the data, you don't want to, it takes so long if you want to take so many points. So you cannot take 1,000 measurements for one data point. Like, it's just not practical, because it literally technically takes time, and you don't want to wait 5 minutes to get one pressure point. You want to do it in less than 30 seconds. So that already limits how many data points you can collect. And so, but you don't want to, but that doesn't limit your resolution, because the resonance frequency, when it shifts across the entire range. Okay. And then because of that, if you fit data, you fit curves with similar amount of error, let's say all of them less than 3%, you can derive like 1,000 points out of that data you've collected. And then when you have the 1,000 data points, you can be really, really accurate in monitoring the change in resonance frequency. And that depends on the algorithm you can program your impedance analyzer with. So we use MATLAB, okay? But if you want to make like a all-inclusive impedance analyzer and interface, you want to see the DSP that you can program in your system, the digital signal processing. That's when the question really becomes, what can we do? How far can we go with this?
And kind of related question, usually when I measure a change in resonant frequency, I tell my students at least to work with phase more than the amplitude.
That's what
in your case, in your case, you use amplitude to determine what your central resonant frequency is. So it'd be good to look at the data and analyze it from phase point of view, change in phase information as well, or both. Both will give you both nice information.
Yeah, I'm sorry if it looks like that, but no, it's phase. Like all of my data is
Oh,
phase.
it is phase. Okay, I thought it was amplitude for some reason. Okay, that's good then.
Mm-hmm. Yeah, I agree with you. Phase is better.
Yeah. Okay, and use both, as a matter of fact. There is a, you know, if you use both phase and amplitude, even you'll get a lot more information.
Also, like mathematically, it's easier to find that minimum point rather than the middle point of an amplitude, because an amplitude is like a slope, and then the middle of it is where the frequency.
That's right.
So it's much easier to find a minimum of a curve than that point in an amplitude.
That's true. With the amplitude, you have to take the derivative and take the slope, or find the inflection point. Usually, that's the easiest way. So that's another one. I guess last question. Sorry, I didn't want to hog the whole thing here. you did the PSP dot, I guess P dot experiments, and you saw the hysteresis loop you looked at, right? And you showed that you're getting a very nice loop, large loops on your CV measurements, right? And this P dot, usually when you deposit this as film, they usually are not solid film. They have a lot of surface area to begin with, right? So how much of this change in increase in hysteresis is it due to just the surface roughness, and how much is it just due to the material itself? Is it kind of, I mean, is it, is there, how much of that, I guess, correlate between those two? Which one would be dominant in this case? I would.
That's a great material science question. I haven't ever seen that being characterized. It's really, I think it's still puzzling for a lot of people to understand what is actually happening in conductive polymers, because now the closest theories that we have modeled PDOT with is, all they say in the literature, material science papers, is that they say PDOT is great because not only it allows the higher transfer of electrons due to the higher surface area, it also allows the movement of charges with the ionic transfer of charges, which is theoretically, when physically you model, there are two different mechanisms that charge can be transferred. So one basically creates an electric fields, and the other one is literally the movement of electrons. So I think when you compare that with like platinum is only transfer electrons. So it doesn't have the ionic exchange of the material. So what happens in this beta is literally like ions are moving, being entrapped again, they get removed, go back to the solution. So it's almost like a exchange of matter happening, like ionic matter, I would say, rather than just electrons. So I know, but how much of it? I'm sure it's changing all the time, depending on how you electroplate it, depending on the thickness, depending on the dopant, depending on your mood that day, what you're doing. So I'm sure it's changing all the time, but I don't know which one's dominant. It's a great question for a material scientist.
And another one also related to that is because P dot usually also oxidizes, is an oxidizer also, right? And the question is, when you go through this, how much is it just due, this loop is due to just oxidation than a true transfer of ions? You know what I mean? So I guess a lot of questions. Yeah, like I said, it's a material science question.
Similar, I'd say again, it's similar question, that the ratio of it is, how much of it is due to oxidation and reduction, how much of it is ionic. I really couldn't tell you. I know it's a mix of them.
Yeah, okay. Those are the questions I had. Thank you. Good.
Thank you.
So,
I think I'm pretty impressed by this presentation. I think one question I may kind of overlooked is that since you are using how about the heat dissipation of the sensor, because you are trying to attach it to potentially human eyes. I may, I didn't see. Do you have such measures of heat dissipation potentially?
No, we don't. You're right. That would be something, I guess, to study down the road, because when we have this electromagnetic coupling, there is definitely some heat dissipation in the sensory coil, and we haven't really investigated that. I think that would be nice to do in future.
Okay. Yeah, I think that's one kind of like potential future work you can do. And another thing is once your device sends something, you might need a mechanism to either store the sense data locally on the device, or transmit it outside, maybe to external device like a smartphone, using probably either wired transmission or wireless transmission like a Wi-Fi or Bluetooth. So I know this is kind of like the first step towards this vision, but do you have any other plan to explore such possibility in the future?
Sure. I mean, it's always desirable to record a few days and then present the data. But in terms of what we've developed, we are not limited by anything. So we are able to continuously create the data using the sensor. But then what happens with this depends on the external electronics that we design, that really this thesis hasn't progressed into that stage so that I could tell you what we have foreseen or projected. But it could be odd. I'm sure it would at some point, that how frequent you want your data to be taken, how many days you want to be recorded before it's presented to the patient, how is it communicated with the clinical professionals. These are all like great questions that we don't know yet the answers.
I think we'll need a collaborator like Professor Zhang to help us develop the wireless interface. So for the data analysis.
I see.
And the transportation.
And we are neighbors too. Our labs are neighbors. That would be nice.
Okay. Yeah, I think that's all my questions.
Yeah, so I mean, in short, the electronics designed by Into Being. So initially we were thinking of adding Bluetooth interface, such that we could, wirelessly transfer the data to a computer. I don't know if they have such features in the current version. I don't think so, because currently we're using SD card for data storage offline, and then we could, collect the data for example, 24 hours, and then just unplug the SD card and then transfer data to a computer. There's no mechanism for real-time data transmission at this moment.
I see.
I had a couple questions going on the other projects.
Yeah, go ahead.
One of them dealt with the optogenetics and the single LED and things like penetration. You think of the thickness of the cortex and penetration, as well as specificity. You talk about wanting to use these to modify behavior, etc. So, if you have this LED on the surface of the cortex, there are many populations of cells there. So how are you going to dissect what cells you want to control versus the cells you don't want to control by something that's just kind of a global stimulation at the level of the surface of the cortex?
Yeah, that's a great question. I always had that myself, and whenever I thought of optogenetics, how can we really specify the cells that we are stimulating? And there are technologies that are trying to, even in Dr. Li's lab, to focus the light, using some lens that we fabricate on the LED. there are ways to control the directions, depth of the light. But what's also possible to employ is the introduction of the virus that, you know, genetically modifies the brain cells so that they respond to light. You can also, to some extent, decide what cells to transfect with, and then select those areas to be optogenetically stimulated when you apply the light. So there are two routes that can be taken, and I wouldn't be able to tell you the extent of each of these, you know, how much. I haven't really dig down into those, but there are still open areas for research. They're both really, really pressing and demanding things to address. Yeah.
Yeah, right. You have multiple viral vectors to transfect different cells. And I assume that in your chip here that you said could run multiple LEDs, that you could run multiple different LEDs instead of running large arrays of a single wavelength. You could do multiple wavelengths, and you could even alter the time frame of those in order to be stimulating cells that have a positive response versus ones that have an inhibitory thing. Ask about the depth, because even in a single cortical neuron, what's happening at the cell body is different from the interaction it has with cells at its apical end and at its distal end. So even an individual cell, particularly in the cortex that spans across the thickness of it, is having different influences on cells over different depths. The other one, I guess, I know we probably talked about this someplace, and that was in that design, and I know it's you know, very first design. What again was the battery life for running the LED? How long would a charge of the battery run before you had to change batteries?
Yeah, I ran one test, like a fully experimental, and it could run like 2 hours of full on with one blue LED using a it was a what size of a coin cell was it? I forgot what size, but I can tell you, like, it's just the standard size you're using, you know, the same coin cell battery for a couple hours.
So
but
chronic stimulation is going to be difficult.
But no, you know, in a real life, like, I didn't blink the LED. It was like on constantly. But when we are applying the light in a real experiment, the DUD cycle is around like less than 10%. That means like less than 10% of the time you're having the LED on, and if you know, and depending on your frequency, again, you are defining how much of an on time you have here, which is it's at least 10 times more. So it's like when I said 2 hours on, so at least for a day you're gonna be fine using like a PWM. That so a day should be okay with the coin cell battery. Before you have to change the battery. But again, this device is also the idea of this device was that the battery is outside, so you can change it easily, like with the smallest intervention behaviorally. So the first idea was 2 towers. The towers come out of the skull, and then you just like insert and then take it off. But then we eventually realized that that's not really robust. So we decided to go with a backpack. So we're gonna have like a backpack. Maybe it could house 2 coin cell batteries on a rat, and then the wires would go underneath the skin all the way to the skull. So there would be nothing on the top of the head, just the backpack. So because the device itself is under the skin.
Uh-huh.
So
in the SECONDSIGHT project, in those arrays, in those arrays, the SECONDSIGHT, are they designing the arrays to take into account the magnification factor of the cortex because you know that the representation of central retina is very compact, and then more peripheral retina, the distribution of neurons is less dense, and so it would seem that the arrays need to reflect the magnification factors of the actual cortical tissue.
That's true. It has been taken into account, yes. I talked to the principal scientists like bi-weekly, and we are always discussing these things. It was really nice. And they have considered, because in the visual cortex, like you said, what happens is that this more central part of our vision has a lot more area covered in the visual cortex than the periphery. So you literally have a map. There are papers that they have mapped this out, and they're telling you that what area in the vision corresponds to the area in the visual cortex, and then they have taken that into account. And so, for example, there are more electrodes of the array focused about the center of the vision, and then so they have compensated that. But the other thing is that what we eventually discussed, this array that is on visual cortex, there is at least 7 or 8 times more area you can cover. Also some parts in the outside of the brain, because this one is going in between the two hemispheres. So there's this external parts of the outside of the brain that are also contributing to the areas that we are, V1, V2, V3, So, and they know that they are not covering most of the areas of the vision. But this was just like a safety study they did mostly. They wanted to see if they didn't want to like create a lot of different external electronics to be able to drive all the area and then to realize it's not safe. So they wanted to just go with what they already had, which was only 60 electrodes in terms of external equipment, and see if it's safe. And it was safe. Like they tested on 6 patients and it was pretty successful. And I don't know if either SECONDSIGHT would reemerge and do that, or another company. It's a great field. I think it should be done pretty soon. Yeah,
it's pretty rational to start with V1 because everything seems to then emanate from V1. So
yeah, I think there's a group at the UCLA. They are doing from the primary visual cortex V1. They're stimulating the V1 area, and I think they're doing the clinical trial now.
On humans.
Yeah, in humans, it's not easy to get at. I mean, maybe it is for the surgeons, but in animals, V1 is up on the dorsal surface of the brain. In humans, it's tucked between the hemispheres. So, yeah, it's a challenge.
The aspect is really good point you raised, because you think and you're like, oh, why don't we put on here or there? But then when it comes to surgery, I asked, they were like, even having 2 of them was way more challenging surgically than just one side. You were like, why didn't you put 2 sides? You could just like left and right. They were like, no, like surgically, it was like they couldn't find an easy way to do it. And I was like, oh, right, okay, yeah.
Well, you have a membrane that's running there, and the membrane forms a venous channel. And if you disrupt the venous channel, you have a tremendous amount of bleeding. And so they probably could detach it from one side of the cortex and slip something in, but to try to detach it from both sides may have been way too risky.
True.
So it'd be interesting to know whether they were doing, were these people that had this implanted, did they have they had vision on one side of the things, they could see things on one side of their visual field improved versus the other side? Since that's the way the cortex works?
Yeah, that's what's anticipated. Exactly, that's what happens, because each cortex.
Actually, I mean, I don't know if they change the patients. The first few patients are completely blind. They don't have any vision in either of their eyes. But they did have the vision before the eyes go blind, so such that they could, you know, they could use the contrast to recognize specific patterns. Because for the first generation, the array only had 16 arrays, electrodes. So the resolution is really poor. And the patients could only see the contrast difference when they scan through the background. If they didn't have prior experience, vision experience, it's really hard for them to understand what they're seeing. So yeah, I don't know if the patient groups have been changed since they, you know, get the approval, but the first couple ones were completely blind.
Yes, what you mentioned is correct for the Argus 2, the eye implant. That's what happens. Like when you're stimulating the retina, you have a lot more room to control and observe what the patient is seeing in terms of directionality, left, right, up, down. But when you go to the visual cortex, especially with this electrode that they got, I talked to one of the patients that had this visual cortex, and they have also written a book about their experience, and so interesting book. What they describe as what they see is almost like they also had vision up until they were 27-year-old, and then they started to get quickly blind for another 24 years or so. And they describe it as almost a new sensory domain. It's nothing like the vision they had before. It's like a sensory domain we don't experience like they do. So that's good for them. But also what they describe it functionally was like the closest thing he could describe it with so that we could understand is they said it looks like one of those radar screens that used to be in you know, airports in 60s or 70s, that there's this like one line that's scanning all the time, and then if there is an object or bright versus dark area, they detect it, but then they have to wait for another cycle. And also it's interesting that cycle is periodically directly correlated with the frequency that they apply these signals, and that's around 8 hertz. Last time I talked to their scientists, so they have optimized it and they realized that 8 hertz is about the frequency that they're stimulating. So there's that sort of new way of sensing that they have. It's nothing like vision. So there's no directionality. To answer your question, for the visual cortex, the patients weren't experiencing really left, right, up, and down. It was just this new thing that they were having. So.
Interesting. Interesting. Okay. Oh.